Hi, my name is Kevin Starr, and today we're going to talk about tank level tuning. In our travels around the globe working in the Process Automation Division, we have found that tank level tunings oscillate. Matter of fact, some statistics have shown that 95% of all industrial tank levels oscillate in some shape or form. And that's why we want to spend the next few minutes showing you some very fundamental techniques that you can use immediately and stabilize your process. What we're seeing here is there's two types of processes that we've talked about before. There's what we refer to as self-regulating. Those are the kinds where you make a change and you get a process, nice smooth response. And from the other videos that we've done, we talk about the process gain and the time constant that define how much it goes and how long it goes. Those are self-regulating. Things like flows, pressures, temperatures, consistencies, those types of things. That's not all your processes. That's about 80 to 90%, which is why a lot of times guys are good at that. But then we move into the non-self-regulating. And so we'll just call them non-self-regulating, or what we're going to refer to as a tank. In this case, it just, whenever I inject it in balance, off it goes. And that's why they're a little bit scary. If you're doing a manual bump test, you have to pay attention. That's why we really recommend that you do a visual inspection. You walk around, you get an understanding of your process before you start doing a bump test. So what we're going to do is talk about how do we identify the process, how do we come up with a model, and how do we come up with tuning rules to identify and to make sure that this loop is properly tuned. Now our process, I'll just draw a little picture here of a tank. Has an inlet flow. And here we've got, let's say, an outlet flow. But in this case, what we have is a controller that is usually it's a fixed. So this is our flow out. So we have our flow out and our flow in. So this is a fixed outlet flow. Maybe it's a drive, maybe it's a control, but it's a constant demand. So in other words, what we've done is we've broken the link between the head pressure and the flow. So in this case, what we have here is if we have a bump test, let's say we have our flow in equals our flow out. In this space, we would say this is balanced. And this would be our level. So that's our level. So when the flow in and flow out are the same, the level doesn't move. Now what happens if I increase the inlet flow? So the flow in is greater than the flow out. Well, what's going to happen is your tank is going to start moving. And now let's say at this point we drop the inlet flow back. So once again, the flow in is equal to the flow out. So we're back into a balanced mode. What's going to happen to the tank level? Boop, it's going to stop. This is one of the ways I like to determine if I even have a self-regulating process. On a self-regulating process, if I put the actuator back to where it was, the process will come back down. So if I draw the rest of this, it'll usually come back to where it started if we don't have stiction and hysteresis. But in a tank, if you put the balanced condition, your measurement will move based upon how long it was separated. This is why we call this an integral type of a process. So you can see it's integrating this difference or this imbalance. That's why these are tricky. So what's the process model? How are you going to come up with model parameters? You can't use the process gain and time constant because it never stops. It never settles. So our definition of process gain as it applies to self-regulating would virtually be infinite. So we have to have a different model. So what we do here in this case is we recognize that there are different slopes. Let's call that M0, M1, and M2. And let's call this change in output 1 and change in output 2. So in this case, what we're finding is that the process gain for a tank is equal to the change in slope over the change in the output. So the slope, how did this change versus that? So that would be this process gain. Let's call that KP1. And then maybe we do again for this one and say that KP2 is equal to M2 minus M1 over our output 2. Okay? I like to do these two process gains because I can also identify if KP1 equals KP2, then I have what I would call a linear tank. tanks can come in all shapes and sizes. You've seen them that look like a cylinder. Sometimes they're on the side so that they have a cross section that changes with the level. Sometimes they look like a cone. So we're going to get into that in our nonlinearity section in a later segment. But right now we're assuming that we have linearity in our process gain. But what I want to identify here is the slope change. So if you remember slope is equal to rise over run, which would basically be the change in level over the change in time. Now this is where, that's the slope. This is where when we do this in classes and we do this in settings, this is kind of hard to do, especially if you have noise on your signal. It's kind of hard to identify. So I recommend that you do this a couple of times, but there's a few things I want to point out here. It's the change in slope, not the slope. I've seen this messed up. If for example, let's say that when I walk up to my tank, it's doing this, and then I do my bump test. Okay, so this is, let's just say this is M0 and this is M1 and this is my change in output 1. I can't just say the slope is equal to that divided by that. It won't give you the right answer. You have to get the change in slope divided by the output. Change in slope divided by the output that produced it. Now a couple things to remember here is your level. Most of the tank levels are normalized 0 to 100, but there are a few that are in feet or meters. So you then have to normalize that. And I would recommend that you look at your industrial books, your technical notes, to determine if the gain needs to be normalized or if they have a factor to do that already. But the time, it also has units. It can be seconds or minutes or hours. What I would recommend is, well, no, it's not recommended. You need to set the time units on your slope equal to the integral time of your controller. So if your controller is working in minutes, you need to do your slope in minutes. If it's in seconds, it needs to work in seconds. I was teaching a class once and a guy came flying in to say, you told us wrong, and he calculated all this, but he had messed up on his minutes and seconds. So he was off by a factor of 60 on his tuning and the thing went crazy. So this theory doesn't work. That's something I want you, the theory always works. Now your implementation of it might be an issue. So what we have here is we're identifying our process. We recognize that a large percentage of our industrial sites are self-regulating. Now we're talking about tank level tuning or non-self-regulating. Where we have an imbalance, we have an integration effect. So we have to kind of, a new term, balance, but we have to calculate the process gain. Now, I always recommend that you link the process gain back to the physical characteristics of the tank. And what's interesting here is that the process gain, let me just start here with, let's draw a picture. And let's say this is my level 0, and let's say this is 100%. So this is my measured value, and this is time, okay? So if I could, and let's say this is my, another one here. Let's say this is my flow in. So here we've got, this is time, 0 to 100. So what we're trying to do here to help you understand what this process gain is calculating is if my flow is 0, I have nothing going into the tank, all right? Now what we do is we take our flow, take it to 100%. So we have 100% of our flow being pumped into our tank. It was empty to start with. We've shut the outlet valve off, so we have an imbalance of 100%. It's the biggest we can get. So what's going to happen to this level? And let's say we time it so that we drop this back to 0. So what we're doing is we are filling the tank. So we have filled the tank. So let's call this a fill test. So this time from here to here is what we call the fill time. The tank fill time. Now I don't recommend that you go and do this. Don't say, okay, Mr. Operator, could you shut all your tanks off so I can fill them up and then time it? That's the idea. If you could, great, but you can't do that. So what we're trying to say is the fill time is really what we're looking at. Is if I have imagine like a garden hose, that you're filling a bucket with. It's going to take a while, but now let's say you got this gigantic hose. How long does it take to fill that bucket? It's a function of the amount of volume of fluid going into it. So the way I like to think of the process gain is it tells me the relationship between my input device and my tank size. If I have a tank as big as this room and I've got a little garden hose, this is going to take forever to fill up. But if I have a tank that's the size of a glass, it'll fill up really quick. So that's why we said, one guy used to say, the amount of time it takes to walk around a tank is real close to the fill time. Now again, I don't necessarily recommend that you go walk around your tank, but this concept that the fill time is what we're after. Well, it turns out that the process gain that we get here, this process gain, which is the change in slope over the change in the output, is equal to 1 over the fill time. So the process gain and the fill time are related. They're inverse of each other. Which that's where we started thinking, is like, well, maybe we don't even need to do a bump test. What if we have our tank here, if I know the volume, which is, pi r squared times the height. And here's my, you've got your level indicator, and you got your taps. So the height's the distance between the taps. And then we have our inlet flow, and we know that, and we can identify the maximum flow. So if I know the maximum flow and the volume of the tank, I can calculate how long it takes to fill that. So for example, if this max flow is equal to 100 gallons per minute, and let's say this volume is equal to 1,000 gallons, how many minutes is it going to take to fill it? 10 minutes. So this would have a process gain of 0.1. So that's how we do this, is I always recommend that after you calculate your process gain, time out and then look at it. Whether you use the slope technique or you use the volume technique to calculate the fill time, go and take a look at the tank and see if that makes sense. I've run into a lot of cases where they messed up the fill time, or they messed up the max. They looked at the span on the transmitter and they had it calibrated wrong. A lot of times this volume, you can go look at the tank, look at the diameter, and you can calculate it. But on a lot of industrial P&ID drawings, they'll have the volume stamped right there on the drawing. So I've gotten this, come up with my process gain, and then I apply that directly into my tuning, and it's incredible how fast you can tune a loop. So if you don't have this information, then you have to do a bump test. If you have this information, I find this to be way more accurate, because the fill time is what you're after. Okay, now that we have the process gain, what we're interested in is coming up with the tuning. So now that we've identified the process, now we need to come up with tuning. Now, what we're trying to do with this technique is, if this is my set point right here, and here's my tank, and there's been a load change, there's been a disturbance of some sort. Let's just say we had a disturbance. So this was a load change. What's going to happen? So what we're saying is, we're running along, someone opened the outlet flow. What's going to happen to the level? The level is going to come down, and what we're going to want to do is, so this is the flow out, we're going to want the flow in to quickly come up to this point. What happens when the flow in is equal to the flow out? The tank stops moving. So what we do is we define this as the arrest rate. All right? So the arrest rate there's a couple neat things about that. That's where the flow in, at this point right here, the flow in is equal to the flow out. In other words, we've balanced it. However, if we stop there, we result in an offset. So control has to keep working. It has to have the inlet flow go above the outlet flow for a period of time to bring this thing back around. And what's interesting, again, we're over here, we're balanced again, where the flow in equals the flow out, we're balanced. It takes 6 arrest rates. This is what we call a second order critically damped tuning for a tank. It's the fastest you can go recover from a disturbance without oscillating. This is the goal. This is what we're shooting for. For you guys that like root locus, I'll real quickly just sort of show you what we're doing here. Because we have a double integrator with our tank, we got our PID control, our proportional integral, and our tank is an integral. So we have a double integral. We got 2 poles. So what happens is, as you start increasing your gain, what happens, and this is where most people mess up, is this is the region a lot of people will leave their control tuning, which means your tendency to oscillate. Now, I don't mean to, if you don't understand root locus, that's okay. This plot sort of shows what happens to the tendency to oscillate as I increase the control gain. So what happens is I start increasing the gain, I start to oscillate. What do we all do? When we're in an oscillation, you cut back on the gain. Well, you cut back on the gain, you just change the amplitude. Well, if you increase the gain, it gets worse. Nobody, by tuning by feel, says, oh, if it's oscillating here, let's just increase the gain a little bit further. That's the reason you need to use the scientific techniques on how to tune a tank, because what we're trying to do is to get over to this area right here, which is what we call the region of stability, which just happens to be 1 over the arrest rate. Okay, so what are we doing here? How do we calculate all this? So when you plug all this math in to come up, the tuning rule is actually pretty easy. We say that the controller gain is equal to 2 over the process gain times the arrest rate, and that the interval time is equal to 2 times the arrest rate. This is the tuning rule for a PI standard algorithm, not parallel or classical, and we've talked about that. And I also want to make sure that if you use, if your level is normalized 0 to 100, you're good to go. If it's in feet or meters, then you may have to scale it. So please look at your technical documentation, but you know, your 2 over KPT arrest or 2 times the arrest rate is your integral time. This tuning technique will result in this type of a response. That's so important that you go back and validate your tuning once you've done it. Cause a load change, watch it stop, and then watch it recover. It's pretty neat to see, and it almost looks like magic when you can tell a customer, hey, it's going to take 6 of these arrest rates to return. Now, for some of you guys that are really interested is how far does this fall? Well, if I know my load change, this change in error, the max deviation, will equal the change in load times, let's see, it's got it. So it's going to equal KPTI over 2 times this E value. So I know it's kind of tough to see, is whatever your integral time is times your process gain, and then your load change. So if you know that you had a 10% load change, you can calculate how far this is going to go. So I've actually come up with tuning like that. If I'm working with a system, I say I can only allow this many inches of movement. Then I say, well, how big of a load change do I have? Once I know the load change this, I can calculate my process gain and my integral time that I need to give me those results. So this is another neat little equation that you can use once you use this technique. Now, this is great, but what people have asked is, how do I calculate an arrest time? And I'm like, well, that's a good question. So how do we calculate an arrest time? Well, when we did our self-regulating, we came up with a tau ratio to try to bias our tuning so that it was a function of our process. What we've come up with is if we say that let's come up with a new variable m and say that whatever our fill time is divided by our arrest rate. In other words, we can flip this around and say that our arrest rate is equal to the fill time divided by m. So, for example, let's say if m is 1. Well, that would be fast or slow. So let me make a little table here, because everybody wants to know fast and slow for tanks. And let's put this m thing here. So if I say m is 1, that is really slow, because that's saying that the fill time is equal to the arrest time. That means that it's going to empty before you even start to try to recover. That's one of the things that I do when I'm analyzing tanks, is I look at this relationship and I know that they've tuned them so slow that any disturbance I have, it's going to empty or overflow before we even come back. You know, maybe I like, picking a 5 to 10. So that we do is we say that our arrest time is 5 to 10 times smaller than our fill time. When we do that, then when we plug this in, you can say that let me put our controller gain here and our integral time here, it's pretty neat. If you take our tuning rules that we had over here for a rest rate, your Kc is just equal to, well, let me just do that here. This results into 2 times m, and Ti equals, it's 2 over TRS, so you can put in, it's 2 fill time divided by m. So now what I like about this is if you notice that that's one of the things with tank levels, you just can't set the integral and move the P for control speed. What happens is this circle literally changes size based upon the type of tuning that you want. So what we have here is this m, this speed is in both components. So if we pick, let's just say 5, what that would do is it would give me a gain of 10, and then our integral time would just be 2 times the fill time over 5. And then if we go down to 1, you would just say this would be 2, and then it would be 2 times the fill time. And then what I do is I usually will build a couple of these, maybe go with 3 and 2, and then I'll fill in my table. And then I come up with the speed of response that is desirable, that gives me the best deviation and the fastest recovery time without overshoot. What we found is this process can actually go pretty fast. Is if you can calculate the volume of the tank and get the maximum flow, you can calculate the process gain pretty quick. And then what I like to do is just to kind of get a feel, is if I take my controller gain times my process gain times my integral time, when you use these tuning techniques, this should equal 4. If it's on either side of 4, it's either going to take forever to get to the set point or it's going to oscillate around the set point. So these are some techniques that we have found when we work with industrial loops. Remember, 95% of all industrial loops oscillate. About 10% of all your control loops are tanks. Tanks oscillating cause an imbalance in your plant, whether it's due to mixing, whether it's due to header pressures, consistency, bonding. There's a lot of issues with tanks that can cause problems when they're oscillating. These techniques first identify the process, whether you do a bump test to calculate the slope, you look at the volume to calculate the fill time, you use these tuning techniques that I'm showing you here. This tuning rule is the rule for tank levels. Make sure that the integral time is a function of your your seconds. If it's in seconds or minutes, make sure that your slope and your integral time are lined up. Then these other things are just ways you can come up with an arrest time that is satisfactory for you and your client. That's our lesson. Happy tuning.